Hello, this is a video on Graham's law of diffusion and effusion. These are for gases only, gas particles. There is actually a technical difference between diffusion and effusion. Diffusion, as you see here, gases are basically just going in between other gas particles, where effusion is a gas particle going through some type of barrier, and they're going through the holes in that barrier. For example, that's why a balloon, if it's not mylar, and mylar is a balloon that doesn't have any holes in it, if it is just a regular balloon, eventually the balloon will decrease because the gas particles have made their way effused through the skin of the balloon into the atmospheric pressure, into the atmosphere. Both of these processes are based on the same piece of information, which is that gas particles are on constant motion. Therefore, if they're constantly moving, they have kinetic energy. And this is what the Graham's law of diffusion is talking about. Now, there are basically, you can look at this law, Graham's law, in two ways: a very conceptual way or a very mathematical way. If you're looking at the mathematical definition for Graham's law, it's the relative rates of diffusion, or you can put in the word effusion if you want, of two gases is equal to the inverse of the square root of their molar masses, or commonly called molecular weight. And I gave you an example. Of the actual mathematical calculation right here. R is the rate of diffusion or effusion of gas A, and RB is the rate of diffusion of gas B. And MW is abbreviation for molecular weight. And I used 1/2 instead of a square root sign because this type of computer program doesn't do square root signs. Okay, this calculation or this equation is derived specifically from the fact that both gases are at the same exact temperature. And as you know, temperature is a function of kinetic energy. So both of the particles have exactly the same amount of kinetic energy. However, something we don't talk about as much is that the actual speed at which the molecule is moving is different because they have different masses. Because kinetic energy is equal to 1/2 mass of the substance times its speed or velocity squared. Usually when we say we're at the same temperature, we say that each particle has the same kinetic energy, therefore it's moving at the same rate or speed. That's a little bit of an incorrect statement. That assumption is the fact that each gas is the same mass. And it works well for all your gas laws. But for this, which is actual diffusion and rate at which the particle is moving in a linear line, you have to take in consideration the mass of the particle. So therefore, both gases have the same amount of kinetic energy, but they're not going to travel the same distance per time, i.e. rate of diffusion, because their masses are different. So again, there's two ways looking at this: very mathematical and very conceptual and non-mathematical. So what I did is I got rid of I dealt with the conceptual and non-mathematical definition first, and basically what that mathematical equation above, the relative rate of diffusion of two gases is equal to the inverse of the square root of the molar masses of the two gases. There's actually an easier way to explain it conceptually, and this is totally incorrect politically. what it basically derives down conceptually into is fat things go slow, skinny things go fast. In essence, high molecular weight or high molar mass substances are slower than low molecular weight substances. Low molecular weight substances will go faster. So therefore, if you are just looking at the relative diffusion rates of two things or several things, and they're not actually asking you for actual numbers, and they just want you to pick which one is the fastest, has the highest diffusion rate of diffusion, then what you do is they're actually just asking you look for all the molecular weights and find the one. If you want the fastest, find the one that has the lowest molecular weight, because that will have the highest rate of diffusion. If you want the slowest, meaning the smallest rate of diffusion, you would look for the highest molar mass or molecular weight substance. Then I give you an example. Which of the two substances diffuses faster? NH3, which is ammonia, or H2. The molecular weight of NH3 is 17 grams per mole. The molecular weight of H2 is 2 grams per mole. So therefore, if you're looking for the faster, the higher rate of diffusion, you look for the lower molecular weight one, which is H2. Then H2 diffuses faster than NH3 since it has a lower molecular weight. And those questions you can answer without actually doing any real math. Okay. For more mathematical problems where they're actually asking you to use the mathematical definition, the relative rates of diffusion with the square roots of the inverted molar masses, there are actually two different types. One where they just ask you for the relative rates of diffusion, in essence. So with that one, it doesn't make a difference if, since it's the word relative, it doesn't make a difference if the rate of gas A is on the top and the rate of gas B is on the bottom in your ratio. However, if they ask you something about how much times faster or slower one gas is to another, then it does make a difference. And what I did is, and I'm not going to talk about it in this video, there'll be another YouTube video that actually talks about it. This section right here is talking about how it's a relative rate. So you could actually answer it in two different ways, as in two different perspectives. And then there's another set here. Again, you get another YouTube video with questions and stuff like that, where it is specific. It actually asks you how much times faster or slower this gas is to that gas. Then you don't have an option. There is only one answer. Okay. And again, those will be explained in different YouTube videos. If you want something that always works for either condition, where it's a relative rate or it's as fast as slow as one compared to the other, the way you do it is you always put the first gas in the numerator and the second gas they talk about in the denominator. In that way, your rate of relative rate problems and your specific rate, as in fast or slow, will always be correct. Okay? And again, that's only if they ask you for specific mathematical calculations. If not, and it's just conceptual, where they're just asking you which one's the fastest, which one's the slowest, or which one's faster than the other ones, then you just look at your molar mass calculations in the highest molecular weight substance is the slowest. Has the lowest rate of diffusion, and the lowest molecular weight molar mass has the highest or the fastest rate of diffusion. Okay. Again, this is all based on that everything's at the same temperature because it has to be, or Graham's law of diffusion